issue from UCLA. So most recently, Harry was with UCLA for a frequently for a couple months. He moved to UCLA. So Harry got his PhD from Ohio State University in 2011. And then went to UCLA to start his academic career. So Harry worked on program analysis, software engineering. Now he's moving to a new field using like a programming language and system techniques in big data analysis. Harry most recently won at ESOP this year. He won the AITO All-Agard Junior Prize. So that's a really nice recognition of his work. So now that's a field from Harry.
Thank you very much for the introduction. And then my laptop just tells me that right now is 1 a.m. in California, so I can literally fall into sleep at any moment during the talk. Just wake me up if you see I'm sleeping. All right, so thank you for inviting me. It's a great honor for me to come here to present my recent work on systemizing static analysis. And it's also a great thing to see so many good friends here again in the community. So during the past few years, my work was primarily between systems and PL, programming languages. So basically, if you look at the existing techniques or work published in these two communities, you can pretty much think of this as a long spectrum with systems on one end, PL on the other end. Systems focus primarily on practicality, while PL focus primarily on elegancy. So what I was trying to do was try to build systems that are more elegant while developing PL techniques that are more practical. Okay, today I'm going to talk about static analysis. Since the community has worked on static analysis problems for decades, right? Like more than 3 decades, 4 decades. So then the first question I'm going to ask here is, has the static analysis problem been solved yet? Different people have different answers. But if you look at papers published in academic conference, like the PLDI or POBL, you can probably find more than hundreds of papers published in the past decade. Like a lot of papers every year. And then one observation you can make over the papers is that the techniques are getting more and more sophisticated, more and more elegant. And although we don't know much about their practicality, there's a reason for it. If your technique is not very fancy or very sophisticated, you get strong rejection from these conferences. Right? But if we shift our focus from academia to industry, one thing you can find is that there are a very small number of commercial analysis tools that are available out there. And almost all of those tools use very simple kind of intraprocedural analysis algorithms to find very simple bugs. And another thing that observation you can make in industry is that industrial software is becoming increasingly large and dynamic. For example, if you consider modern big data systems, and most of those systems, like for example, this entire Apache Hadoop software stack, most of the systems have a million lines of code. And it involves multiple components written in different languages, and those different components interact with very complicated protocols or interfaces. So, in other words, papers are going more and more elegant, while tools that get appreciated in the industry are going more and more practical. So there seems to be an ever-increasing gap between these two communities, and this gap is actually getting larger and larger. So then the question here is that, why do we have those problems? What prevents papers published in academic conferences from being applied to industry settings? So here we see 3 major problems. The first problem is scalability, as everybody here knows, right? So in many cases, I wouldn't say in all cases, but in many cases, the more sophisticated a technique is, the more poorly it scales. Right? It's especially true if you consider industrial software that all has million lines of code and are very complicated, and finding anything useful there is very difficult. So the second challenge here is difficulty in implementation. Right? So most of the algorithms coming from academic papers involve very complicated logic dealing with various precision, scalability, or precision performance trade-offs, like the ones that Mike just presented. Very complicated, making themselves hard to implement and maintain in an industrial setting. So for example, if a company wants to implement an algorithm like this, they have to always have a group of people capable of understanding and even publishing papers in those academic conferences, which is very difficult. So the third challenge here is difficulty in dealing with multiple languages. Like I said, smarter software all has multiple components written in different languages. So it's very difficult. Like for example, a typical example here is Android. Right? Android has a Java world and has a C world. If you look at static analysis tools developed for Android, pretty much all of them focus on Java. Right? But if you really want to understand deep bugs, for example, bugs related to memory management or power management, you have to analyze the two worlds together to understand how multiple components get involved in a complicated decision-making process. So I'm not saying that our community is not aware of these problems. So actually the community is well aware of these problems, as has been trying to come up with solutions for decades. Right? So for example, to deal with poor scalability, the community has been trying to develop algorithms that can trade off precision for scalability and minimize the amount of information generated for decades. Right? And the downside of this kind of approach is that the more, like I said, the more sophisticated an algorithm is, the more complicated the implementation is. To simplify the implementation effort, there's a great line of work done in the community by Yannis and other people that try to use decorative models like deadlock to express static analysis problems. This is actually a very good idea, so that the developers do not have to worry too much about the analysis implementation. The only thing they need to do is to describe this algorithm in terms of the deadlock interfaces. However, these techniques are fundamentally limited by the deadlock engine that we use. If you look at deadlock engines used in this community, most of the engines were developed by other communities, like database communities, right, for general purpose usage. They're not designed and implemented specifically to satisfy our needs. An example here is that many of the static analysis problems are graph reachability problems, right, that exhibit strong locality. But if you don't want to change an existing deadlock engine, chances are that they couldn't really deliver this desirable performance and scalability considering those locality information. So, as I said in the beginning, I've been building systems for a number of years. So here's some perspective when I'm putting on my system builder hat. So basically, this slide shows some numbers which demonstrate the sizes of some real data sets that the system people in industry are dealing with every day. So for example, the physical graph had about 68.7 billion edges, like 6 years ago. And this number might have just tripled, or doubled, even tripled over the past like 6 years, 7 years now. And Google Maps had about 20 petabytes of data in 2015, which is also a very big number. The reason why I want to show those numbers is because if you compare those numbers with some of the largest programs that we consider in our community, we can see the differences, right? So for example, the Linux kernel, actually one of the recent versions of the Linux kernel that we studied, has about 16 million lines of code in its code base. And if you perform very aggressive function lining, like you line everything from the top all the way down to the bottom, you end up getting a program graph with about 1 billion edges, 1 billion edges, right? HBase, which is an Apache project, is a distributed system with about 1.37 million lines of code. If you perform aggressive method in lining, you're going to end up getting a graph with about 128 million edges. And Hadoop even has fewer edges. It is fully inline version. So what I mean by this is that if you compare those numbers with this physical graph, for example, then you might think that we're just little kids playing with toys every day, and the question we're asking ourselves is that why do you actually complain about scalability? Because it's not really large compared to industrial data sets that people are dealing with every day there. So this observation led me to think that the reason why we didn't have very useful, very scalable analysis tools is probably not because our programs are too large, or because we don't know how to come up with sophisticated algorithms, but instead is probably because we haven't thought about how to develop scalable systems that can automatically parallelize and scale the program analysis workload. So if you look at the design and implementation of most of the existing big data systems, then you can see that all of those systems fall into this category. They follow this formula, which I call big data thinking. So what does this mean? It means that, first of all, if you have a large data set, and second, if your computation is simple enough, then you can actually develop systems that can automatically parallelize and scale the computation to the large data set. So then the question is, can we formulate our static analysis problems into this big data thinking and then develop systems to automatically parallelize? And I'm going to tell you how to do this in the next few slides. But before going to the technical details, let me first tell you a list of things that we should and should not do when thinking about this formulation. The first thing is, please leave the algorithm simple. Don't develop very complicated algorithms. Like I said, the more complicated the algorithm is, the more difficult it is for the system to automatically parallelize it. Right? Ultimately, we need very simple computation running on the top for us to develop a system. And second, don't worry about too much intermediate data. This has been a fear to us for almost 20 years, right? So if you look at existing techniques, they all try to develop some complicated algorithms, try to minimize the amount of information generated. But in this case, we don't have to worry about this much intermediate data generated because we can leverage modern computing resources like fast CPUs, like fast SSDs, or even large cluster supports to deal with the data explosion problems. And third, if you want to use an existing system, like a data log engine, don't stop at the interface between the application system, right? Because if you want the system to deliver the performance and scalability, you better go into the system and change it for our specific needs, instead of just treating it as a black box and hoping that it will actually give us the performance scalability. That's not going to be the case, right? So, or we can even design and implement new systems to satisfy our specific needs. So following this big data thinking, what we've been doing is we actually built two specific systems in the past few years. The first one is called Graspan, the second one is called Grapple. So both of them are single machine disk-based systems, specifically designed for the static analysis workloads. So for example, Graspan is a graph system designed for CFL-reachability computation, while Grapple is a new system for finite state property checking of very large-scale system code. Before talking about these specific systems, let me first give you some high-level idea of why the systemized static analysis will work, will solve those problems, as I mentioned before. So first of all, the developers no longer worry about memory blowout, as we have disk support, right? As long as you know how to partition a big graph into smaller partitions, and how to develop efficient algorithms that can perform efficient swapping between memory and disk, scalability is no longer a concern, right? And second, by pushing the work of tuning from the analysis layer down to the system layer, the implementation effort can be significantly reduced. So because the analysis developers now only need to implement a few interfaces, they no longer need to worry about performance and the scalability. The system worry about it. And third, because our systems are taking generic graphs as input, components of different languages can actually be transformed into graphs of the same format and analyzed together by our system. So automatically we have this ability of dealing with multiple languages. So let's first look at the Graspan, which is a graph system developed specifically to perform parallel and efficient computation of context-free language reachability. So for those of you who don't know what CFL-reachability is, I can give you a very quick 1-minute tutorial. So basically, the idea is very simple. You have a program. The program is turned into a graph representation in which variables represent the vertices. Sorry, vertices represent the variables, and edges represent assignments. Right? Each edge has a label representing the type of the assignment. For example, whether it's a variable assignment, or is a heap read, or a heap write. Right? Those are the types. And then the developer specify a context-free grammar G with balanced parentheses properties, like K goes to I1 to L2. The basic idea of CFL-reachability is to perform reachability analysis over this program graph P. Then we repeatedly find paths on which the sequence of labels match one of the grammar rules specified with the grammar, so that we can add transitive edges. Right? In this case, for example, we have a pair of consecutive edges, A to B, B to C, labeled L1, L2. Then you compare the label sequence with this grammar rule, then you see that we can add a transitive edge from A to C, labeled K. You keep doing this until you reach a fixed point. So, CFL-reachability has a wide range of applications, starting from data flow analysis, through push-down systems all the way to set constraint problems. Among those applications, the most well-known or most useful one is probably pointer alias analysis. I'll show you a very simple example of how alias analysis can be done by using CFL-reachability. If you have a very simple program that looks like this, B equals A, C equals B, then you know that we can simply design a grammar that says this, right? Alias goes to a bunch of assignments, right? So the intuition here is very simple. If you perform a sequence of assignments, variable assignments, then the end variable should be the alias of the beginning variable, right? That's it. And then this graph shows a graph representation corresponding to the program. You have two edges from A to B, B to C, labeled assigned, and you'll match the sequence of labels with this grammar rule that you say, hey, we have a transitive edge from A to C, labeled alias. So basically, A and C are aliases. What if we have complicated constructs like address off and dereferencing? It's simple. So we basically have to augment this grammar with a additional rule that says alias goes to ampersand, alias star. So the intuition here is also very simple. If you take the variable, you get the address. You propagate the address along a sequence of assignments. At the end, you do a dereferencing, right? And you end up getting the same value, right? The value at the end is the alias of the value at the beginning, right? So this is the graph representation corresponding to the program. Based on the previous slide, we already know that B and C has an alias edge. Then you basically compare the sequence of edges, labels, ampersand alias star with the second rule here. Then you see that we should add a transitive edge from A to D. There also exists an alias relationship between A and D, right? So then the question is, how do we formulate static analysis problems like CFL-reachability into this big data thinking, as I said before? So let's look at this algorithm or this formula again. So it basically says if you have a large data set and your computation is simple enough, then there's an opportunity for us to design a system that automatically delivers the parallelism and the scalability. So our insights of turning code analysis into data analytics are as follows. First of all, we perform aggressive link lining on the input program. So we end up getting a graph which is completely 100% context sensitive. So we end up getting this context sensitive program graph, which will be used as the input of the program, right? So this gives us two benefits. Number one, our analysis computation is very simple because it's automatically context sensitive. Number two, the graph is big enough so that satisfies the first condition that you see from the formula. During computation, we choose to add transitive edges explicitly instead of treating them implicitly, right? So this basically means that at the runtime, during computation, you can have a lot of edges added, extremely large number of edges added. Right? This number can even be bigger than the number of initial edges that you have in the initial graph. Right? So that gives us an even bigger graph to deal with. It's essentially an evolving graph problem that also satisfies the first condition, which is large data set. By doing so, the core computation gets simplified significantly to just adding edges. You don't have to doing label matching. You don't have to do a lot of those complicated kind of logic there. The only thing you need to do is to repeatedly add edges, which simplifies the computation significantly and satisfy the second condition, right? Which is kind of simple computation. But of course, if you do this, you're going to expect a memory blow-up. We don't need to worry about memory blow-up because we know how to leverage disk support. Then the question here is that can you directly use one of the existing graph systems? Because there's so many graph systems out there. Can you directly use one of those for this particular workload? The answer is no, because Now the graph systems support dynamic addition of a lot of edges. So if you consider something like GraphG, that does support dynamic addition of edges, but the support is very limited. So we have two specific needs here. One is for the online edge duplicate check. We have to perform very quick online duplicate check. The second need here is that we have to repartition the graph dynamically, because otherwise the graph can easily go beyond the memory capacity. And my Frank McSherry here, actually, ETH, has been trying to convince me to use a general data flow engine, like a differential data flow, for this particular need. I haven't tried it yet, but he reported that like the differential data flow engine can actually give us even better performance than Graspan. But it's definitely something that is worth looking at. So let's first look at Graspan. So Graspan is a scalable and parallel data flow graph system built specifically for static analysis. And it's very easy to implement static analysis on top of it. So this is what Graspan gives us at a very high level. It takes two pieces of information at the beginning. So one piece of information is a program graph. The second piece is the set of grammar rules. And eventually it produces a graph at the end with a lot of dynamic edges added. So Graspan's design has three different components: a pre-processing component, edge pair-centric computation component, and a post-processing component. Pre-processing basically partitions the graph. It partitions the input graph into a small number of smaller partitions. And each partition is defined by a vertex interval. And physically, each partition contains edges whose sources fall into that interval. And all the edges in each partition are sorted based on their source vertices for locality purposes. And then there's a loop here involving edge pair-centric computation and the post-processing. So the edge pair-centric computation works in super steps. As the name suggests, each super step loads two partitions from disk into memory and tries to join, essentially it tries to join the edge lists from the two partitions based on the vertex IDs and the labels. As you can see from the picture, we use very concise representation for representing those partitions. All the edges that have the same vertex are grouped together in an edge list. For example, you have these edges from 0 to 1, from 0 to 4. They're grouped together in this edge list pointed by vertex 0. And A, B, C, D, those are labels. If you look at this graph, you can see that we have two edges, 0 to 1, 1 to 2, labeled A and B, that match that grammar over there. That means that we should add a transitive edge from A to C. From 0 to 2, labeled C. So this picture basically shows the scenario in which a lot of the new edges are added, including that 2C there, right? So all the edges are added in a very special way so that they get appended at the end of the edge list for its source vertex, right? We also distinguish old edges from new edges added in the same iteration because we want to avoid a lot of redundant work of matching old edges with old edges, right? Another thing you can see here is that different threads can process each edge list completely concurrently without needing any synchronization. This is actually a very typical example of a BSP-style parallel computation. So at the end of each iteration, we basically repeat this over and over until the delta becomes 0. And at the end of iteration, the Graspan advances to the post-processing stage in which we repartition the oversized partitions to maintain balanced load on memory. And then the partitions are flushed into disk files. And eventually, we have a scheduling algorithm that tries to load two new partitions from disk into memory for the next round of computation. To choose partitions to load, we have a scheduling algorithm that favors in-memory partitions and partitions with higher matching degrees. So for example, if you can reuse an already in-memory partition, you can save quite a bit of disk IOs, right? Another thing is that this matching degree is the metric that will compute for each pair of partitions, indicating how many edges can potentially match from these two partitions. The higher this degree is, the more edges, the more opportunities we can find for adding transitive edges. So basically, there are a bunch of heuristics that we use for scheduling. So using Graspan, we have implemented a fully context-sensitive pointer alias analysis and a fully context-sensitive data flow analysis. We ran these two analyses on 3 programs, a recent version of Linux kernel, a PostgreSQL database, and an Apache HDBD server. And all of the programs here are written in C programming languages. As you can see later, this Graspan infrastructure can be easily extended to analyze Java as well. And all the experiments were run on a Dell desktop. It's a low-end Dell desktop with only 8 gigabytes of memory and 1 TB of SSD. So it's a rather low-end kind of configuration that you will see for your development desktop, for example. So for the evaluation, we asked 3 questions, basically, 3 major questions. The first question here is about the usefulness. Can the interprocedural analysis that we implement improve, for example, dozen endless checkers? You know, dozen endless have implemented a bunch of checkers, like 20 years ago almost, to find bugs in operating system kernels. We're trying to see here whether the results from interprocedural analysis can improve their checkers. So we basically augment their checkers with the results of our analysis. We found 85 new null pointer bugs and more than 1,000 unnecessary non-tests in Linux kernels. And also, there are a lot of false warning that get reduced by, to get eliminated by using more precise analysis results that I didn't have space to show here. If you're interested, you can read the paper for the details. The second question here is about performance. So how well does Graspan perform? So the computation time has a large range. It ranges from like 11 minutes all the way to 12 hours, depending on the program structures, depending on the analysis that you implement. But for all cases, the computation successfully ran to the end. And the third question here is, how would Graspan compare to other systems, like GraphQL that I mentioned earlier? We tried GraphQL, which was built by a group at SMU like 5 years ago, and GraphQL, at that time, GraphQL was the only system that could support dynamic addition of edges. So we basically picked GraphQL as our baseline engine, and we see GraphQL crashed in like 133 seconds. Then we also try to implement traditional algorithms using work lists ourselves and ran those algorithms on a large server. Remember that our experiments were run on a small desktop. But if you implement those traditional algorithms, you have to run it on the larger servers, because otherwise it will run on memory very quickly. But even if this implementation were run on larger servers, it still ran on memory in most of the cases. It's very interesting. We tried deadlock engine like Socialite, and it also ran out of memory in most cases. There are some other probably better social deadlock engines available, and also this differential data flow system like Naiad. I haven't got the time to try them yet, so I definitely will have my students work on them.
Excuse me, quick
Yes,
question. What does
sure.
in most cases mean? You ran it on 3 programs, right? In most cases means
Oh,
3 or
those 3 programs and a bunch of checkers. We have this static, we implement 2 analyses, right? We implement the context-sensitive pointer analysis. We implement the context-sensitive data flow analysis. And then we ran each analysis on each program. So that gave us like 6 combinations, right?
Thank you.
Yeah. So now we'll move on to talk about the second project, Grapple, which is a finite state property checker. It's a system for performing finite state property checking of large-scale systems code. The very motivation for us to pursue this project is that it's based on this observation that many bugs in large-scale systems have finite state properties. Examples are, if you're familiar with Dawson Angler's classical SOSP 2001 paper, you know that many of the bugs that he found and his group found in the OS kernel are finite state property bugs. So for example, misplaced locks or used after fray memory bugs and so on and so forth. There are a lot of those finite state property bugs. After about 15 years, if you read the recent study on bugs in distributed systems, you can see most of the bugs studied in that paper, in that SOC paper, 2015-14, most of the bugs studied there are also finite state property bugs. So examples are socket leaks. There are a lot of socket leaks in distributed system implementations. And task state problems, like a typical big data system also often has a scheduler that works with a task graph, right? If there's anything in your implementation that is not specified by the task graph, there's a bug. So And there's also bugs with, that are caused by mishandled exceptions. It turns out that mishandled exceptions are a very serious type of bug in distributed system implementations, because those systems execute for like weeks and months. If you have any exception that is mishandled or unhandled, you can crash a node, and it might bring the whole system down for a long time. So how do we find those bugs? So the idea is very simple, right? So first of all, the developer specifies a set of types of interest, like files, like I/O, or exceptions, and so on and so forth, as well as a finite state machine specification of the possible type, possible states, and the transitions between those states. And then our static analysis analyze program to extract sequence of method calls on each object of each type, and compare those sequences with this FSM specification to see if there's any violation, right? So that's the kind of the basic idea, which is very simple. To implement this checking, we need three different analyses, actually two different analyses. We need an alias analysis to resolve alias relationships. We also need a data flow analysis that can track precisely the object flow to identify state transitions. To report fewer false warnings, to basically make our bug report more precise, we need both analyses to be fully context sensitive and fully path sensitive, right? Context sensitivity guarantees that different objects do not get merged in the same flow, while path sensitivity guarantees that we're eventually reporting bugs with respect to particular control flow paths, and those paths are indeed feasible, right? So Grapple, this is not a new problem. Again, this is not a new problem. It's a rather old problem. There are a lot of people in our community who have worked on this problem. Like Alex Aiken has a tool called Saturn that can actually perform path-sensitive property checking. The tool was developed like almost 10 years ago. This is not a new problem. So our contribution here is not to develop sufficient algorithms or like on any of the algorithmic part. Our contribution is actually to demonstrate that it's possible to develop a system that can automatically parallelize the existing analysis. Okay, so Grapple has three phases. The first phase performs fully path-sensitive, context-sensitive alias analysis. The second phase performs fully path-sensitive, context-sensitive data flow analysis, using the results from the first phase to resolve aliasing relationships. And eventually, we extract command sequences to find bugs. As we already know, both context-sensitive alias analysis and context-sensitive data flow analysis can be formulated as a CFL-reachability formulation, right? Can be formulated as the context-free language reachability problems. And we already know that Graspan is pretty good at performing the CFL-reachability computation in a parallel and a scalable manner. So, the first thing that we do to develop Grapple, we're going to adopt this edge pair-centric computation model from Graspan. The unique contribution here in this work is how do we represent and solve path constraints during graph processing, right? Because in order to implement path sensitivity, you have to represent and solve the path constraints. How are you going to stick those path constraints into the graph engine? That's the biggest contribution of this work.
Question?
Yes?
So, for like this event sequence that you extract, like, you get them from the property or?
Yeah, we basically analyze programs. The event sequence are.
But you get them from the property. They have a property.
Yeah, we have exactly. Yeah, we have properties. Properties are defined by the developers.
Okay, and so the events are what's mentioned in the property.
Yeah. Thanks. So before talking about how we represent path constraints, let's first go over graph representations and a computation model for Grapple, right? So our graph representation here is very similar to the graph representation for Graspan because of the reuse of that computation model there. So each vertex still represents a variable, and each edge represents assignment. So what is different here is that each edge carries additional piece of information, which is this label C there, which represents the constraint of a control flow path leading to the assignment, right? So before adding a transitive edge from A to C, we now have two conditions to check. Number one is an old one, which is whether the sequence of labels L1 and L2 match a grammar rule, which is the same as Graspan. The second one is whether the conjunction of the two Boolean formulas, C1, C2, is satisfiable. So when we add transitive edge, we have to make sure that this transitive edge represents a path-sensitive assignment, right? So if both conditions are satisfied, we add the transitive edge from A to C, labeled K and C. K is this non-terminal there, and C is the conjunction of these two Boolean formulas. So the challenge here, like I said before, is how to represent the path constraints and incorporate the path constraints into graph processing. So if you're familiar with existing graph systems, you probably know that for existing systems, each edge only carries fixed size data. And right, so then the size is often very small, like smaller than 4 bytes, right? So for space efficiency, because otherwise your system is going to have huge space problems. So then how do we add for each edge a path constraint which is supposed to be a large formula, which can be arbitrarily large, right? So this is the biggest challenge. Our idea here is to use a statical representation of a control flow graph called the Interprocedural Control Flow Execution Tree, or ICFET, as the index edging. So instead of letting each edge carry a long Boolean formula, we let each edge contain the path encoding, which can be used at the runtime to query this ICFET to give us the actual path constraint. So that's actually the basic idea. So let's first look at the control flow execution tree. If you have experience with symbolic execution, this tree structure looks very familiar to you, probably, right? So each node here represents a control flow basic block. Each edge here represents a control flow branch. So for example, node number 0 there represents the entry basic block there, and it has 2 branches, fal and t, represent, for example, this 2 node number 2 represent the basic block for this for the true branch of the conditional x greater than 0, while this false branch leading to a node number 1, which represents this false branch of that conditional, right? And then each basic block might correspond to multiple nodes here in the tree representation, like 4 and 6, both represent that basic block there, and each representing a particular control flow path leading to that basic block. So the basic idea is to lay out explicitly all possible control flow paths in your function. This is the intraprocedural control flow execution tree, right? So that we construct for each method. And then another special thing here is that each node has an ID. And we use a very simple numbering algorithm to generate the IDs. Like the ID for the top node is always 0. And then for its false branch, the ID is computed as its parent ID times 2 plus 1. And then the ID for the true branch is computed as its parent ID times 2. Those are very simple computations that can be done efficiently by doing simple bit shift, right? So based on this tree representation, we can encode an intraprocedural. Again, we're talking about the intraprocedural now. Later, we're going to extend this to interprocedural. But for intraprocedural CPaths, control flow paths, it can be encoded uniquely as a pair ID start and ID end, right? Where ID start is the ID for the starting node of the path, while ID end represents the ID of this end node in the path. Decoding can be done very efficiently by essentially doing a backward traversal on this tree, starting from this end node, right? Every single step, all you need to do is to get the current node's ID, do a bit shift, that's going to give you the parent ID. You keep doing this until you hit the the starting node ID. Then you recover this entire path, right? And we use loop unrolling to handle loops, which is pretty standard. And the other thing is that we use symbolic execution to compute symbolic conditions. And we store those symbolic conditions with each branch there for us to quickly compute an intraprocedural path constraint at the runtime. So in order to encode an interprocedural path, we first have to compose a bunch of intraprocedural CFET into an interprocedural CFET by connecting caller and callees at the call sites. For example, in this case, we have 2 functions, f in the bar, f calls bar, f this call site f2. The way that we cook them up is that, if you look at this picture, at node number 2, which represents the basic block containing the call site, we add a bunch of call and return edges connecting this to ICFET, like intraprocedural CFET, right? So we have a call edge going from 2 to node number 0, which is the entry basic block in the callee, and then we have a bunch of return edges connecting each of the leaf nodes in the callee back to the call site node in the caller. And all of the nodes are labeled. Like for example, if you look at this call edge, it has two pieces of information on this label. The first piece represents a symbolic equation representing parameter passing, right? And the second piece represents the call site ID. So the first piece of information, it will be used to construct the constraint for this whole pass, while the second piece of information will be used to perform a context-sensitive traversal of this graph. So based upon this representation, an interprocedural control flow path can be represented as a sequence of intervals, right? In this case, for example, we have 20, 25, 20 that uniquely identify this path, marked, highlighted with stars in the picture. The first 20 and second 20 encode these two fragments, path fragments in the caller and the callee respectively, while the 25 in the middle represents this call edge. So basically all the call and return edges are uniquely numbered. We can use those IDs to dynamically identify those edges. So you can see that this sequence has variable lengths, but is fundamentally bounded by the call stack depth, which should be much more concise than representing this control flow path. So based on this representation, we can dynamically, at the runtime, compute the constraint for an interprocedural path by decoding those intervals and getting their intraprocedural path fragments, computing their constraints, and putting all of them together into a conjunction form, which will give us the final constraint for this entire interprocedural path. Okay, I'm going to skip this slide, which is about computation, and I'll go talk about the evaluation. So we implement 4 different checkers, actually, and run them on 4 large programs, like Apache Zookeeper, Apache Hadoop, HDFS, Apache HBase, which are all large-scale distributed system implementations. And the 4 checkers we implement include I/O checker, socket checker, exception handling checker, and lock usage checker. The checkers have about like 3.2 thousand lines of Java code, while Grapple backend itself has about 13,000 lines of C++ code, with about 1.5 thousand reused from Graspan. So 2 plus 1 postdoc and 5 students, 1 year of effort to implement it. And this basically, we ran the 4 checkers on each program that we have in our set. This slide shows the bugs that we found for each category. RE basically represents the real bugs we found. FP represents the false positives. We carefully inspect each warning generated by a tool and then distinguish it as distinguish the real bugs from the false positives. So Grapple eventually reported a total number of 359 true bugs and 17 false warnings, with a pretty low kind of false warning rate due to our precise handling of paths and context. And this picture basically shows the performance. Like this is the number of vertices in the beginning, number of edges in the initial graph, number of dynamically added edges, and this PT represents the pre-processing time, CT represents the computation time, TT represents total time. So total execution time, again, has a very large range. It ranges from 2.5 hours all the way to 19 hours. To have a deeper understanding of the performance, we basically break down the execution into 4 different components: I/O, constraint lookup, SMT solving, edge computation. And you can see that for 3 programs, Zookeeper, HDFS, HBase, edge computation, which is completely in memory, takes the majority of the running time. While for Hadoop, SMT solving takes 70% of the execution time. This is primarily because of the program structure. If you look at Hadoop, you can see a lot of those long interpretive paths. So eventually, the path constraints that we end up getting are very complicated. So it takes the SMT solver a huge amount of time to solve them. Okay, at the end, so this is the last slide I have. Hopefully, at the end of the talk, I've convinced you, I don't know if I've convinced you, that a lot of those static analysis problems that have given trouble for us for a long time, like probably decades, can actually be solved if you shift your mindset from developing sophisticated algorithms to developing scalable systems. And we believe that there are a lot of more problems are amenable to this big data thinking. So for example, right now we're investigating the possibility of developing a distributed system for scaling set solvers based on Spark. So both systems are available online. So if you're interested, you should try them out and send me your feedback. Thank you very much.
Let's take a couple questions from the audience.
Yes, there's a question there.
Yeah,
Thank you. These are very inspiring systems. I have just basically a clarification question for slide number 9. If you can go there, you were saying that in developing the system, you shouldn't be afraid of generating intermediate information.
Right.
Our computation resources will handle this.
Right.
What do you mean exactly by that? Because, for example, on slide 29, you have many systems actually run out of memory, and isn't this the very problem that we're trying to solve when we are scaling the analysis?
Right. So I think what I meant by this was, first of all, we have those, I think it's here, we have those massive amounts of computing resources that are available these days in modern computing if you know how to use those resources. Like a large cluster, like SSD support, or like a large amount of memory, if you know those resources, you should not be limited in the single machine memory, right? And rather, when you develop algorithms, your focus should be how do you simplify the computation so that the computation becomes simple enough that it can be run and automatically parallelized by an underlying system. This is what I meant by this. I don't know if it makes sense to you. But.
Right. So if I can rephrase you, you're arguing for simplifying the computation and making it more streamlined.
Right. Yeah. So I'm arguing for pushing all this complexity in from the analysis layer down to the system layer. Let the system deal with it. And the analysis layer, you only implement a few interfaces. Kind of like what people do with graph systems. Right? You have a system that automatically takes care of this tuning or parallelism, but at the developer level, they only follow a few interfaces. And as long as you have those interfaces implemented, then the system takes care of the performance tuning and other things.
Thank you.
I think there's another question here.
Okay, go ahead.
Oh, okay.
Sorry, quick question. Asked the question on the previous one. On the slide 25, you mentioned that
you take notes.
I guess you can just press 25 and then or something.
Really? I don't believe that.
Okay,
That's
never mind.
hard.
You guys can talk offline.
All right, yeah, sorry.
Okay,
That seems to be very detailed question.
Okay.
Right, that's the quick question.
Yeah, so my question is, so the decision precision that you described for the first graph processing system is exactly the same in Datalogue. It's called semi-naive eager evaluation, right?
Yeah.
So my question is, you say you use 1 terabyte SSD, and I can buy a machine with 1 terabyte RAM now.
Yeah.
So why would I use such kind of processing systems and not just buy more RAM? How much would I need to have the?
Yeah. I think this is a very good question, and I usually have this kind of questions when I give a talk in system conferences only. Right? So, for example, if you say if you talk to HP people, they never buy any argument of doing doing distributed systems because they can have those gigantic machines with multiple sockets that can hold like terabytes of memory, like even petabytes of memory. They can do that. I think there are different kind of usage scenarios, and there are different kind of trade-offs you can play with. So in this system, we basically focus on like small, low-end development machines. So I don't know if it's true that Google has so every single developer in Google has this kind of 1 terabyte of memory in their machines.
We have one here.
Oh, okay, that's probably true, but I don't know, right? But what if you have, and another thing is that a lot of this big data processing now goes into labs, right? A lot of the end users are like bio experimentists, right? So they actually do a lot of experiments.
How much do you use from this 1 terabyte? Do you actually need 1 terabyte?
Yeah. We have some experiments we use quite a lot of those disk space, yeah.
And if it's RAM, would you make it with 1/4 of it? Do you use compression on it? Do you use some other?
No, we don't use compression. Oh, we do have some compression. Yeah, we do have some compression at the disk level, definitely. Yeah.
Okay, guys.
Yeah,
Sounds
we
like
can
we're going to
definitely
have some additional interesting discussions afterward. Let's thank Henry for the talk.